preferred directions. And this allows you to explain why such travel maximum mixing can come about in that exception. S4 are basically similar things, but it's a bit more complicated. I don't have an example for S4 actually at hand, but it is. Well, actually, this here is an example for indirect models. And for indirect models, as I said, it's not. We don't have this very strong relation between this kind of remnant symmetries. But we rather want to kind of what we need is groups which have triplet representations. And A4 is the smallest group which has these triplet representations. So it's actually the simplest one that one can use for indirect modeling. So that's why I think it's quite attractive. And it works very well to get something like this here, like that one. The model building with direct model approach, this is what really prefers S4. The other things normally go a little bit different, so I'm not going to give an explicit example. I think it's you kind of have to arrange the symmetries get broken in the different sectors in the right way. And then everything else is completely automatic, makes no sense. But yes. The problem with this okay, we'll discuss this. Okay, one comment I would like to make, which is also a big distinction. When you think in terms of this indirect models, the situation that you normally have is that is family symmetries that completely broken in both sectors. So that's a big difference. So it's like when you have this direct model, you really need to arrange that these remnant symmetries remain in these two sectors. Whereas here, the only important thing is that these kind of flavor vectors, because the analytical fields point in the right directions. And then everything works. So you have to take care that there's some symmetries are preserved. And this is also not happening normally. So you break all the symmetries completely. And okay, now when you think in terms of remnant symmetries, and you have to explain why θ13 is now not 0, it's 9 degrees. Then this whole mechanism breaks down. Because you cannot work with the same symmetries. I mean, you have studied this exactly these are symmetries which really correspond to travel maximum mixing. So now you go to different groups which give you different predictions. So it's kind of, this group is very firmly connected. You have some smaller breaks normally in these models, but it's really in this strict approach you have to find a different symmetry. You have to find a symmetry which works with this. And people have of course explored the whole space of possible symmetries that you can use to explain θ13. And there are symmetries which can come close, but they get very, very big and very, very complicated. So in some sense you cover almost the whole space of possible mixing angles with if you just go to more and more complicated groups. But it is not as easy as it was before, that you just have everything points to S4, you implement S4 and you can try maximum mixing back and everything is fine. So it's getting really very, very complicated. In some sense, the feeling is that it almost has stopped searching for these groups because they found groups which come closer and closer in the group space, or in the space of group possibilities. But it's the question of what you're really learning when you go in this direction. But maybe there is one group which has been overlooked and which can explain everything. But at the moment, I don't see a very simple possibility to continue with this direct modeling approach. This is what I would like to cover very soon. Okay, so yeah, there's another thing. Before I come to the issue of θ13, I would like to discuss with you another interesting thing about family symmetries, namely the possibility to also explain why the neutrino spectrum could be crazy to generate. Because if I remember, so there's three possibilities. You can have a normal hierarchy, which is the M1 much lighter than M2 and then M3. So this is a normal hierarchy. You can have the inverse hierarchy where the M3 is much lighter in the M1 and M2. But if the absolute neutrino mass scale is larger, then you have the situation that M1 and M2 and M3 have masses which are very close to each other, and there's only a very small mass splitting between these three mass eigenvalues. And this is something which there is some prejudice that this is not very natural, because you would have to tune these masses to be very, very equal to each other. And in fact, yes, when you think in terms of the type 1 seasonal mechanism, I don't regard this as a very generic possibility. Because if you just consider you have the three contributions from the three right-handed neutrinos, and if the Yukawa matrices are kind of hierarchical, and the masses of the right-handed neutrinos are kind of hierarchical, then why should these three contributions be really exactly of the same size, or almost exactly of the same size? So how can you explain such a crazy degenerate spectrum? But there's a possibility when you have a type 1 plus type 2 seasonal mechanism. We discussed yesterday that in left-right symmetric models, this is actually quite generic. So you have these two possibilities. Either have a pure type 1 mechanism, or if you have these triplet generations to break down to the standard model, you get a type 1 plus type 2 seasonal mechanism. So you have these two contributions. Now what is happening? Is the following. When you again take the left-hand doublets in triplet representations of some family symmetry group, like you just did it with A4, or you can also take SO3 group, then you can get a type 2 seasonal contribution in leading order, which looks like this here. Right? So this, but now, since these two here are triplets, you have to contract these two triplets here to 0. So this means you don't have the Yukawa matrix anymore. You just have one value here, and you can form Yukawa coupling, and this flavor structure here is completely diagonal. So you get a type 2 mass contribution. This is just this Yukawa coupling, this small in this left, or this left couple, this left in the triplet, times the unit matrix. So if you have this family symmetry here, you get the unit matrix contribution to your total neutrino mass matrix. So the structure that you have is something that we call a type 2 upgrade, because you can have here your normal type 1 seasonal model, which determines the mass splittings and the mixing. So this here can, for instance, be travel maximal mixing form. And then you can simply, by having this extra type 2 contribution, and you don't have to do anything else. It's just the way that you assign the electrons in triplet representations of your family symmetry group, SO3, A4, give you this extra contribution here, proportional to the unit matrix. So you can explain why the mass matrices are almost equal, just with this contribution. So this here would be kind of dominating here. When you are in the regime that you have crazy degenerate neutrinos, you have one equal mass scale, and then with this here, you generated a small splitting and also the kind of mixing. So when you have a mass matrix like this here, and you just add the unit matrix on top of it, it is not necessarily changing the mixing structure here. So you can very nicely have control of the mixings and mass splittings, and just increase the neutrino mass scale. You can also do this with travel mixing models, for example, and it works. You can comply this with quantified theories, with the left-right symmetric quantified theories. This is one of the two generic cases that you have this extra type 2 contribution. That's why I would say there's no reason to have any prejudice against crazy degenerate neutrino masses. And as I was mentioning in the first lecture, there's this hint from the Boss experiment that maybe they have seen that the sum of neutrino masses is around 0.3 electron volt plasma response, provided the constellation experiment is this. So, but this has to be confirmed, of course, by the different experiments. Or if neutrinos double beta decay experiment sees something, they would point to a crazy degenerate spectrum. So at the moment they're probing the crazy degenerate neutrino mass regimes. And you can explain this really nicely with this kind of mechanism. And that's another application of capitalism. But now let's come to the issue of theta 1 stream. And in fact, it is interesting that so far I've just discussed about family symmetry models independent of great unified theories. But already in the times when people try to combine family symmetries with great unified theories, we're noticing that they're not getting exactly trial maximal mixing. So people kind of have tried very hard to, also with this direct model approach to combine it. It's difficult and you can manage, But especially in the indirect model approach, very often it has turned out that you get an extra contribution to the mixing from the charge leptons. So here in the neutrino sector, you can realize Traube maximal mixing. But since you have this strong connection we discussed yesterday between the downtown quark matrix and the charge lepton matrix, so these may be right, or Cartesian models, they may be equal or related by this Clebsch-Gordon factors that we discussed yesterday. You expect also that there is some kind of mixing in here. So it would be kind of strange that we have mixing in the quark section. And as we discussed at the beginning, even the Lebo angle, so the 1-3 mixing in the quark sector is normally coming mainly from the down quark mass matrix. So you expect that you have a large 1-2 mixing in here. And by these calculations, you also expect that you have a large 1-2 mixing in here. This is it's getting a bit more complicated. These mixings are not equal because we were discussing that the masses of downtown quarks and charge leptons cannot be equal. So you need some group theoretical factors, some Clebsch-Gordon factors that give you the right mass relations. But nevertheless, it was always expected that some mixing comes from here. And of course, in the total PMNS mixing matrix is the product of the left diagonalization matrix of the charged leptons times the left diagonalization matrix of the neutrino spectrum. So you need to look like what is the product by neutrino oscillations. It's just this product here. You cannot get it separated, but you can assume that here, the neutrino spectrum we have, for instance, Traube maximal mixing. Or some other prediction you can derive. So that's not the only special structure. You can also have bimaximal mixing there, for instance, or something else. Then you have corrections coming here from the charge. Okay, so this is quite generic, and if you have, if you assume that in the charge lepton sector, as we just discussed, this 1-2 mixing is the biggest, and 2-3 and 1-3 mixings from the charge leptons are smaller. That's kind of similar hierarchy between the mixings as we had in the down quark sector. And we may think of this as being related to the down or 1-2 mixing or 2-3 mixing. Okay, then what do you get out of this? I mean, you have to calculate this here. You have here for the neutrinos, you have the Traube maximal mixing matrix, which has a 1-2 and a 2-3 rotation. And then you add on top of this here, you add a 1-2 rotation from the charged leptons. So you have a 1-2 times a 2-3 times a 1-2 rotation. So in order to bring this in the right order, you have to commute the 1-2 charged lepton mixing with the 2-3 neutrino mixing. And these two matrices, of course, don't commute. If you commute a 2-3 rotation and a 1-2 rotation, what you get is a 1-3 rotation. And you get a change of the 1-2 rotation. That's just by the commutation observations of these rotation matrices. Okay, so this 1-3 rotation you deduce is, if you take for simplicity a maximal 2-3 mixing in the neutrino sector, just 1 over square root of 2 times this 1-2 mixing from the charged leptons. So you're inducing a 1-3 mixing from the charged lepton corrections. This is one thing, and the other thing is you're also correcting your 1-2 mixing, of course. So you're commuting, and then you're kind of subtracting from the 1-2 mixing in the neutrino sector. And now the interesting thing is that you can find is that this gives you this relation here, and there's a phase coming in. And this phase which is coming in here, this relation, is exactly the testable Dirac P phase of the PMNS matrix. So you have this here, which one we call a lepton mixing subgroup, that you have 1-2 mixing PMNS minus theta mod 3 cos delta. These are measurable quantities equals the 1-2 mixing in the neutrino sector. and if you have a Traube maximal mixing here, then this side here should add up to 35.3 degrees. So this is the value for Traube maximal mixing. So this is a nice thing of this paradigm, that 1-3 mixing comes from the charged lepton, is that here you can generate the right size of theta mod 3. I'll come a bit later what you need for this. But then in addition, it allows you to test your hypothesis that you have Traube maximal mixing in the neutrino sector, or any other difference that mixing here. So you can reconstruct in some sense, purely by measurements, by neutrino oscillation measurements, elements, you're mixing in the neutrino sector, which can give you very interesting information. So this here, if you measure these quantities and it comes out to be 75 degrees, then I think that would be a quite good hint that maybe there is indeed some underlying maximum mixing structure. I know, yeah, I will come to this soon, yeah. So at the moment, I think the hints for data are not really conclusive. Yeah, error bars are still quite large. And this actually means, I think that this formula was not so strong when θ13 was small, so this would not be a big correction. But now θ13 is 9 degrees. We really know that this cost delta has to be small. Otherwise, you get a too big correction to θ12. So this means that thermal maximum mixing can only work if you have 90 degrees or 270 degrees, such that this cost is small. And this is I think, a good way to test this kind of line of thinking with underlying thermal maximum mixing plus charge level. Yes. Okay. Now more specifically about this, the size of θ13. And here it's basically when you now take some downtime mass matrix of this form here, where we have again a 0 to the 1, 1 element, as we discussed at the beginning, which may be quite useful. And then, as we discussed yesterday, the charge Lambda mass matrix has a similar form, but in these elements, you can have Clebsch-Gordan factors, two theoretical factors, which give you the difference between this matrix and this matrix. And here I should write this down. Here in the context of SU5 models here, for example, where there's the relation that the MD equals the MD transpose modulo this kind of Clebsch factors. And now if you calculate θ13, then this here is kind of 1 over square root of 2 times 1, 2 mixing here. And this is just the ratio of this Clebsch factor times 1 over square root of 2 times, when you also use the relation to get that in the right masses, times the Cabibbo angle from the Quark sector. So in this, if you take θ Cabibbo over square root of 2, this is approximately 9 degrees. So it's 9 degrees times the ratios of these two Clebsch factors. And so it turns out that the only thing that you have to arrange for is that you have equal Clebsch factors here for these x into y elements. And this is indeed consistent with group mass relations. So there are example choices that you can put here, that the first and second family of quark-lepton mass relations come out just right. And that you have two equal Clebsches, which can give you exactly this, that you have the θ13 mixing basically explained by 1 over square root of 2 times the Cabibbo angle, which is about 9 degrees. And this would work, and this can work quite nicely. So I think that this is kind of interesting. So the next thing is that, if you want to also be consistent, like we've seen for the case of thermal maximum mixing, you would like to get also some predictions for the Dirac CP phase, FFP&S. I just want to be very briefly here. So the idea is that you also generate the phases of your column vectors when you do this breaking, like we discussed in this kind of macro alignment. When you assume that you have spontaneous CP violation, this means that the original symmetry before you do this kind of macro alignment for analytical Weber vectors is completely CP symmetric. And just by these macro expectation values, which are, because we have complex scalar fields which can be complex, you can introduce CP phases. And there are also nice mechanisms which can, for instance, explain why the CP phases can be kind of 0 or 90 degrees, like we did this in the quark section to explain this quark phase, and like I was discussing just at the beginning. And they have a similar, when you have such a vacuum alignment which gives you kind of purely real or purely imaginary entries, then it turns out that very typically in models you also get the same for this charge lepton phase delta 1 to charge lepton, which then turns into prediction for the delta P of an S phase, the Dirac P phase here, which are also multiples of 90 degrees. So these kind of things, and they have been realized in various models, can also be just a prediction of your flavor models. So it can work nicely together with the quark phase rule and this kind of Leffler mixing rule that you have the right combination here of these phases, the specific values like 90 or 270 degrees. So there's a hint in the data, a very slight hint, as was just mentioned, that maybe the delta phase is around 180 degrees, which also again has to be confirmed. But if this was actually true, this would also have some very nice implications. Namely, if there's, in addition to starting with double maximal mixing in the neutrino section, you could as well also start with bimaximal mixing. So bimaximal mixing got much less attention when the data was so close to double maximal mixing because theta was really small. But if you now apply this Leffler mixing rule to a theory which predicts bimaximal neutrino mixing, bimaximal neutrino mixing would be the theta 1, 2 neutrino, theta 2, 3 neutrino. So just in the neutrino section, not the total P1S angles, would be pi over 4, so maximal. And so you have 45 degrees, and theta 1, 3 neutrino would be 0. That's called bimaximal mixing. It can also be realized quite nicely. In particular, if you have an inverse neutrino mass hierarchy, it can be realized quite nicely, as we did also in this paper, for instance. And yeah, now we have to be compatible with about 35 degrees, and we know that the theta 1, 3 is around 9 degrees. And now the opposite case is there. So you need a large correction here from the second term. And this can actually work if you have the delta P of S equal to 180 degrees. But yes, and it turns out 180 degrees. So the science is such that 180 degrees works fine. So this is a second possibility, and very distinguishable when you can measure in the future the Dirac P phase. So that would be another smoking gun if you would have an inverse neutrino mass modeling and the Dirac P phase 180 degrees, such that this here works. That could also be implemented nicely in the brain. Okay, last slide I have here. This is just showing again this Leffler mixing rule in a more general context, which gives you this. This is the formula here where you can reconstruct the theta 1, 2 neutrino by a measurement of the Dirac P phase, taking the data. This is from 2012, but that will change too much. And as you can see, when you measure a certain value, then you can just see what would be the underlying theta 1, 2 neutrino value if the conditions for this Leffler mixing symbol are satisfied. And you see that here there will be special values for 180 degrees. You would be in a situation consistent with bimaximal mixing, 45 degrees. And for 90 and 270 or minus 90 degrees, you would be here that is trimaximal mixing value. And if you would measure something around 0, that would basically exclude both of these possibilities. So you can nicely test this hypothesis that you have some underlying bimaximal and trimaximal. Okay, just as my last statements, I think it remains very, very interesting when these measurements are going to come about the neutrino mass hierarchy or the Dirac P phase. Also, the value of theta 2, 3, if it's now larger or smaller than the maximum, will be very interesting. Also, more precise measurement of theta 1, 2 is very interesting in testing this kind of models. So, in order to make further progress, it will be fascinating to watch what is going to be found in the future neutrino oscillation experiments. So this is the end of the lectures. If you have any more questions, just catch me later during coffee. And I hope you enjoy the lectures, and thank you very much.
Thank you very much for wonderful lectures. So, any urgent questions? You can wait until the coffee break.
Arguments for the shaping symmetry can also be applied to the quark sector.
Yes.
So you can mention it's a larger family group more complex scalar, and so then we can construct the generators corresponding to the clock mixing. So then we can guess a larger signature group, then we can unify the pocket sectors. In principle, this can be done.
Yes, surely. I mean, in the sense of indirect models, so there is basically now the progress that these models are constructed in the sense of grand unified theories, and there we have quarks and leptons unified, and we have the shaping symmetries and family symmetries, which works for the quarks and the leptons together. So we are generating the structure, we are using this group theoretical factors from GATS to get the right mass relations, and this works nicely together. The status is at the moment that still these models, that's basically what you kind of was thinking. It goes to quite large kind of shaping symmetries. So we need many of these additional symmetries that help to get the right structures. I think that there's a lot of work to do in order to make this more simpler and maybe more convincing. But I think it's definitely possible. There are also quite complete models which are quite predictive on there, but yes, I think more work to be done to make it simpler, more elegant. And of course, also the future experiments will probably tell us where we went wrong and we have to improve. It's kind of a development that's going on.
Okay, so other questions? So,
yeah, that's something I did not discuss, I did not mention. Actually, this is not especially given by anything. So it is a free scale in these kind of models. So it may even be quite close to the TV scale, and then you can get again have the chance to maybe observe the flavor sector and scalar fields in some way. But on the other hand, there is no reason to explain why it should be so low. So if you have a grand unified theory, the expectation is more than it may be also it's a little bit higher energies. But unless you have a more complete theory, you don't know where this goes.
I have questions. So in your lecture, you didn't address much about inverted or normal hierarchies in model theories. So you want to say something about that?
Yeah, I did. I was a bit brief on this. This is, if you go back to this kind of example that I showed, I made a small comment where you want to look at the normal hierarchy model, which explains this with a trial maximal mixing in the neutrino sector. And this here is a reference of the model where you look at. You're just using exactly this kind of strategy. So if you have trial maximal mixing, and then this goes very well together with a normal neutrino plus hierarchy, you're using this constraint sequential dominance. You only have these two column vectors, and you have this kind of hierarchical neutrino column matrices. This works nicely. But there's also a nice possibility to construct an inverse neutrino mass hierarchy in grand unified theories, which there's also some kind of prejudice for at least with many people. It's kind of not natural. So because the quarks mass matrices are hierarchical, so you also expect to have hierarchical neutrino mass matrix or a normal hierarchical. But this is actually quite easily possible because you have the right in the neutrino sectors. Because if you have a symmetry right in the neutrino sectors, actually you become kind of crazy. You become crazy Dirac structure there. Then you can also explain the neutrino, inverse neutrino mass object. And if you want to have more details, so this is maybe you look at where this kind of mechanism is explained. So I think both of them work nicely. Yes, I see some slight preference that the trial maximal mixing inverse pattern is normal hierarchy. The inverse pattern is Y maximal mixing here. But this is maybe only these two examples. I don't know if this is extremely general. But both of them can be constructed. And then for the crazy general spectrum, I said that definitely would point maybe to type 1 plus 2 C-squared, which also works nicely left-right symmetric and unified theories. So there, all these three possible spectra, I think, can be very well realized. But they point to somewhat different